How are we doing? We're only on our third-ish ionic compound problem, and I bet you're feeling much better. So we aren't told these are ionic compounds, but we know they are because we have metals and non-metals, and this is not the only way. I'll show you how to determine what kind of bond it is. But we haven't learned any of the other ones yet, so we'll get there. We'll get there. All right. So using these shortcut charges. These are the charges of the ions that are formed from the elements because of their valence electrons, right? That those metals are going to lose those number of valence electrons, giving them those charges. And on the non-metal side, we got our noble gases aren't going to form ionic bonds. The halogen is going to gain 1 electron to get that octet, gain 2, and gain 3. Okay, so let's go right into the problem. Potassium. K has a 1 positive charge. I'm going to use the crisscross method for all of these, and I'm not going to color code these metals and non-metals anymore. You are good enough. Sulfur, right over there. Potassium is number 19. It's kind of right there. There we go. So sulfur is going to have a 2 negative charge. Let's crisscross just the numbers, not the charges, and we get a formula unit of K2S. There's our formula unit for that. And then I'll just, why not, just draw that out here. K2S, okay, so we got 2 Ks, 2 potassiums, 1 sulfur. And let's move the valence electron from the metal over to the non-metal, and we get potassium. Put the brackets there, emphasize that. That's a cation. There's 2 of them. Sulfur. It's going to now have the 8 dots because we're showing the valence action. Potassium's got a full energy level too, but so there we go. No structure for potassium sulfide. Anions end in IDE now, right? Calcium. Didn't we just do this? No, we didn't. We used it as an example. Coulomb's law example, I believe. All right, those big Q's, huh? Big charges. Here we go. Calcium, 2 positive. Oxygen, 2 negative. All right, here's something new. Crisscross the numbers. You get 2 and 2, right? We do have to reduce. Sorry, my bad. I didn't tell you that. Now you know. All right, because these are not molecules. These are not discrete molecules. They stretch pretty much infinitely in all directions. So we've got to find a unit of that repeating thing. So we're going to reduce these. So the formula unit, I need to tell you this tomorrow. There's the formula unit. Got to reduce. Think about it. If you have 2 calciums and 2 oxygens, that's the same thing as 1 calcium and 1 oxygen. All right, there's my valence electrons for calcium. There it is for oxygen. Let's move them to the cation or the metal, to the non-metal, making the cations and the anions. 2 positive, 2 negative. Bigger Q's. Bigger Q's means higher melting point, higher lattice energy, that kind of stuff. All right, moving on to C, sodium, right there. You know, it's got 1 valence electron it's going to lose, so it's going to have a 1 positive charge. Oh my, that's nitrogen. All right, sorry about that. Oxygen, we just did that. 6 valence electrons, going to gain 2 electrons right there, crisscross. Formula unit, Na2, oh, that's sodium oxide. All right, so we need 2 sodiums for every 1 oxygen. Sodium's got that 1 valence electron. Oxygen's got that 6. Let's move that from the metal to the nonmetal. They are in love. It's a love story. Na. Oh, but there are two of them. Oxygen. Show that valence. There's one of them. There's your lowest structure for sodium oxide.